Hello and welcome to this lecture on chemical process modeling and simulation. In the previous lecture, we learned about the various variables that go into uh, the construction of a chemical process model. Basically, the stream variables, the input-output stream variables, unit and process variables. So, in this lecture, we are going to focus on the constraints that exist between these variables. These constraints will be expressed in mathematical form, and therefore the final set of constraints that we write would serve as the mathematical model for that set of processes that take place in a given unit or a set of units. So in the formulation of chemical process models, this lecture is going to focus on the constraints. And one thing to keep in mind in this lecture, we are not going to derive all those relationships that exist between the variables. For example, we are not going to sit and derive the various conservation equations. We are not going to derive the equilibrium relationships between various phases and so on and so forth. And we are not going to define all the rate laws that exist as equations. Right? So this lecture actually is going to serve as an introduction to the constraints that can be written between the various variables. All right. And in a series of lectures that follow this, we will be looking at the different types of constraints in more detail. So to orient you to this lecture once again, I present once again the block diagram, which sort of serves as a representation of how a chemical process model is formulated. So you have your input variables, stream variables, output stream variables, unit and process variables. All of this we discussed in the previous lecture. Now we are going to focus on the constraints that exist between these. No real problem exists without constraints, and this is something important to recognize. A problem is specified under a certain specific circumstance, which means you define the various conditions and under which this problem exists, and therefore those themselves are constraints. Constraints may be on input stream variables, output stream variables, unit variables, process variables, or the combinations of these variables. First off, it is important to recognize the relationships between these variables, particularly the equality constraints, meaning some equation that relates one set of these variables to another set of these variables. There are a number of equality constraints. We are going to look at them in some detail. One of the examples that I want to give upfront is one of definitions, where you define some specific design variable, process variable, for example, right, as a function of some other variables. Now here is an example: residence time in a mixed tank system, stirred tank system. It is the average residence time at steady state is defined as the volume of the system divided by volumetric flow rate of the stream that is coming in and going out. So the volumetric flow rate is a stream variable, volume is a unit variable, the residence time is a process variable, and there is a relationship between these three variables. In a large process, however, when you have a flow sheet, for example, so you have multiple units that are lined up one right after the other, and the input to one particular unit is basically the output from a previous unit. So all the specifications that come up, so once you've solved for a previous unit, when you are going and simulating, developing a model and simulating the next unit, now what are you doing is the output from the previous unit is fed as input to the subsequent unit, and therefore the entire input becomes specified. All those specifications are also really constraints on the problem, so they should all be listed as constraints. You remember, at this point I want to recall the modeling recipe. We have to list all the variables that we did in the last lecture, and list all the equations. We are trying to sort of introduce to you the various constraints, and we'll make a list towards the end of this lecture. Now, you define the degree of freedom as the difference between the variables and number of variables and the number of equations. Then all the rest of it are independent variables that will have to be specified. So here what I'm really saying is that the output from one particular unit, when it is fed as input to the next unit, so the specification of the input stream to the next unit is basically captured as constraints which will fulfill this degree of freedom. Right. Further, there are also limitations to what the maximum allowable variations in any of the variables can be. For example, in a reactor, you will typically have a limit as to what the fluctuation in temperature can allow to be. If, for example, in a distillation equilibrium stage, distillation tower, there will be some allowable variation in the head of the liquid that is present above the tray, which essentially will determine the residence times involved, which will determine the flow rates involved, and so on and so forth. So there are these limitations in terms of maximum allowances that you can allow in the control process. And this could also result from competing reactions. So when you have multiple reactions that take place, so you don't want to allow the conversion of a secondary reaction to exceed beyond a certain point. And you will have certain production demands that will say suddenly you may have to produce a little bit more or a little bit less. All of these constraints may end up getting expressed as upper and lower bounds on variables. And these bounds are all inequality constraints. So a temperature has to be within, say, 180 degrees and 185 degrees. There is a 5-degree range that is allowable, and that mathematically, when expressed, becomes an inequality constraint. 180 degree less than T less than 185. So that becomes an inequality constraint. How do we then express essential physics mathematically? Now we are now looking at the broader picture of the various constraints. Remember, in the last lecture, one of the last lectures, we talked about how it is critical to capture the essential physics, chemistry, or biology of a process. And for that, we need to first understand the physics, chemistry, and biology of the process, and understand at what scale we are trying to look at the process and model the process, and accordingly decide what is the essential. Now, once we capture this essential, we have to express this essential physics mathematically. Fortunately, all processes follow some fundamental principles that can be enshrined in 3 categories of mathematical relationships. One is conservation laws, which are laws which describe how a certain quantity is conserved through the process. The second type of mathematical relationships are constitutive relationships, which basically sort of give expressions for the various parameters, various quantities that exist in the conservation laws. For example, suppose you are looking at energy flux, that you are looking at conservation of energy, and in the system you have energy flux through a solid. Now you have to define how does the energy get transported through a solid. The mechanism, the essential physics, is one of conduction, and there is a law called Fourier's law of conduction, and that is a constitutive relationship that relates the rate of a process, which is energy transport, to a driving force for that process, which is the temperature gradient across that solid, and it captures the resistance offered by the system, by that solid, to this transport of heat, which is captured in the parameter thermal conductivity. And this relationship is a constitutive relationship. Like this, you have a variety of laws that you have studied in chemical engineering. All of those fall under the constitutive relationships. The third one is, of course, the variable definitions. Like, for example, what we saw in the previous slide itself, a couple of slides before, how residence time is defined as a process variable is defined as a ratio of a unit variable and a stream variable, right? So this kind of variable definitions. So all the processes, when you are trying to capture the essential physics, chemistry, or biology of the process in a mathematical form, you can look at those mathematical forms in one of these 3 different types. And by applying these principles judiciously, we can develop a sufficiently rigorous formulation, mathematical formulation of a process. So this is what we are going to try and do. This is what you are actually done in various courses of yours in whether it is CRE or reaction engineering or mass transfer or heat transfer or fluid mechanics or mechanical operations or whatever be the courses, thermodynamics, all these courses, that is exactly what you've done. You've tried to write conservation equations, individual terms you've tried to define using some constitutive laws, and wherever certain parameters show up, you have used definitions, and therefore you have arrived at a mathematical formulation that describes whatever process you've sought to describe. None of this is really new. I'm just trying to codify all of this into one set of principles, so that when you go and look at a new process that you have hitherto not studied, you have a list of sort of a checklist of how to go about doing things. That's the objective behind all these lectures so far. So if you look at equality constraints fall into three broad categories. One is the kind of conservation equations. You have overall material balance or species balance, energy balance, momentum balance, and then you also have certain properties that are constant across, that are fixed across interfaces like temperature, pressure, or chemical potential as part of equilibrium. These are conservation relationships. And then you have to define the various terms in the conservation relationships. You have to write rate equations sometimes. The rate could be rate of a physical process, something like thermal conduction that we just talked about, or momentum transport, or species transport, or it could be a chemical process, which could be a chemical change, which could be a reaction, all right, a chemical reaction. And then you also have various other equilibrium relationships that pertain to phase equilibria or reaction equilibria or surface interfacial various equilibria that could be coming up. These together form the constitutive relationships. In these equilibrium relationships, you have, for example, the equations of state that you've studied in thermodynamics, the various activity coefficient models that you've studied in thermodynamics. On the one hand, the equilibrium relation tells you that for phase equilibrium to exist, chemical potentials of each species that is in equilibrium across phases must be equal across the phases at the interface wherever the equilibrium exists, right? So how do you define this chemical potential? To define this chemical potential, you would have written some either activity coefficient model based relationship that you would have derived, or equation of state based relationship that you would have derived, right? Fugacity coefficient or activity coefficient and so on and so forth. So all of those are constitutive relationships. And then finally, design variable definitions, which is, for example, the definition of residence time that we just saw, right? So basically these three types of relationships. Now, what I had said in the previous slide, conservation relationships, constitutive relationships, and definitions, a little bit more of examples of what types of relationships fall under each category. Now, if you were to look at conservation relationships, these relationships are exact. If energy is conserved, energy is conserved. Material is conserved, material is conserved. Momentum is conserved, momentum is conserved. There is no approximation in this. All right. On the other hand, constitutive relationships are approximate, and they are dependent on the nature of the system and its behavior. We will see this in some detail in the forthcoming lectures, when we have an exclusive lecture on constitutive relationships and the general basis on which constitutive relationships are typically framed. We shall see that in one of the forthcoming lectures, but I would like to point out, for example, you have studied in heat transfer itself, there are two types of constitutive relationships that you've studied for two different mechanisms of energy transport. One being conduction, you have written Fourier's law of conduction. The other being convection, and you have written Newton's law of cooling. Right? Take Fourier's law of heat conduction, for example. The law essentially states that the rate of the physical process called energy transport by conduction is proportional to the temperature difference across, temperature gradient across the system. Now, why only temperature gradient? Why only the first derivative? Why not the second derivative? Why not the third derivative, and so on and so forth? Why not write a Taylor series out of it? Um, one may ask such questions, and you will notice that if you go back to original Fourier's papers and see how Fourier arrived at this relationship, it would have been by a set of experiments that were conducted. Now, another constitutive relationship that I would like to bring to your attention from, for example, thermodynamics is the ideal gas equation. At constant temperature, pressure and volume follow an inverse relationship with each other, which is essentially Boyle's law. And how did Boyle come up with this relationship? You would see in your school textbooks that they will say that Boyle conducted various experiments, and then he found that there was this inverse relationship. P was some constant by V, and so on and so forth. So sort of rectangular hyperbola type behavior. So this oftentimes these kind of constitutive relationships are obtained from experimental data, and a functional mathematical form is fit to the experimental data. So one other example that you can probably recall is how Cp, for example, specific capacity or density or viscosity, all these thermodynamic or transport properties become functions of temperature or functions of pressure, and so on and so forth, and you sort of express the dependence of specific heat on temperature by some empirical relationship. All those empirical relationships are also constitutive relationships. All this such curve fit data that you take, and then you fit a curve, and then you get the best fit, which again another reaction engineering, all the order of reactions. So you write first order kinetics, second order kinetics, all of them are approximate, right? So all of these are approximations. Where do these terms go? In your conservation equation, when you write a species balance, for example, you have to write say a flux for diffusion, which would be your fixed law of diffusion, and then you will have to write an expression for a reaction, which could be a first order kinetics. So basically, while the species conservation is exact, now for each term in that conservation, you are saying that, okay, you know what, this is how much of that species goes into this particular way of leaving or entering the system, which is basically, one example is diffusion, and the other thing is this is another way by which the species enters, or in this particular case leaves the system. The species undergoes a chemical reaction and forms a different product. So both these quantities that you are writing are not exact, because your laws that you're using are approximate. And so a conservation equation is an exact conservation equation, but the individual terms and the numbers that you plug in there are approximate, and therefore the mathematical model becomes an approximate representation of a process that is taking place in a system. I hope I'm able to connect this with the first definition that we wrote for a or we presented for a mathematical model, and that connection has to be made clear. Where does the approximation come from? And of course, before even getting to this, to writing the conservation equations and the constitutive relations, you have to look at what scale you are modeling the system and what is the essential physics. There itself one level of approximation comes, and here is the next level of approximation that comes. So as I said, this is why the mathematical model of a system becomes an approximate representation of the system. If you look at the conservation laws, the quantities that are conserved in any non-quantum process, that's what our focus is going to be, are mass or material, which is species, energy, momentum, and momentum could be linear momentum or angular momentum depending on the nature of the process. Additionally, when a system is in equilibrium, in other words, there is no further change in its properties unless disturbed externally, there are certain conserved quantities like temperature, pressure, and chemical potential. These are the thermodynamic criteria for thermal, mechanical, and chemical equilibria respectively. In one subsequent lecture, we will be sort of considering a generic system, chemical system, and then we will derive this criteria for chemical equilibrium. So the number of such criteria is the number of systems work modes plus one, and plus one, that one is for heat. This is oftentimes called as state postulate. If there are m phases and n components, you will have the various conservation equations for basically, sorry, the temperature is constant across the phases, pressure is constant across the phases, and chemical potentials of each species, the chemical potential is constant across the phases, and these together constitute the set of equations for chemical equilibrium. So these are conservation laws. If you are looking at a conservation law of any specific quantity, not during equilibrium, but when there is a non-equilibrium situation, the following template is generally observed. The rate of change, either accumulation or depletion of a quantity in a specific region, is rate of the quantity going into the region minus rate of the quantity coming out of the region plus rate at which that particular quantity is created in the region by what are called sources, and minus rate at which the quantity is consumed in the region by what are called sinks. All right, and this is a classic way of what is called Eulerian way of looking at a system, where you define a region, a control volume, then you look at what comes in, what goes out, and this leads to the writing of what you have done in all your chemical engineering courses called shell balances. Shell species balance, shell momentum balance, shell energy balance, shell mass balance, right? And then you write this form of an equation, then simplify the equation and obtain a particular conservation equation, right? So in this, actually what we will end up doing in a subsequent lecture in this course would be that we would not look at necessarily this kind of a specific shell balance approach. We will derive conservation equations from a slightly different approach. We will discuss that in a later lecture. To close this lecture, I want to talk about sources and sinks. So in the previous slide, you talked about how, we talked about how a quantity could be generated in that region, in a region where you are writing the balance equation by some sources, or it could be consumed in that region by some sinks. So what are these sources and what are these sinks? Sources and sinks are the cause of what is called divergence in a system, and that we will see in greater detail later on. Sources and sinks are modes of generation and consumption of conserved quantity respectively. From the general template, it is apparent that the boundary of the region may act as both source and sink, so something coming in and something going out. So there will be a generation, suddenly something is coming in, the boundary is putting something into the system, or the boundary is taking something out of the system. But outside of that, what are the other sources and sinks that are possible for various conserved quantity? For total mass, there is no source. Again, keep in mind this is a non-quantum process, so you are not going to convert mass to energy. So there is no sink for mass as energy, or vice versa. Component mass or species, yes, you can have a source of sink by way of chemical reactions. So you can produce a new species or you can consume a new species. You can exchange species within subsystems, and you can by way of diffusion, by way of migration, and so on and so forth. Energy, by mechanical work you can produce energy or consume energy. By viscous dissipation, friction, you can produce or consume energy, and by work done through other modes and thermal conduction too. All right. Momentum, that is pressure gradient, that causes bulk flow. There is shear stress that causes specific momentum transport between layers of fluids, and then there are body forces such as gravity. So all these are possible sources and sinks, and using these, based on these sources and sinks, there could be a generation or consumption of various quantities. So with this, we come to the end of this lecture. Thank you very much for listening to this lecture. If there are any questions, please post your questions in the comment section, and I'll be very happy to get back to you. Have a wonderful day.